We now get to Chapter 4, Atomic Structure. We're going to look at now counting atomic particles. So this is a periodic table. It's amazing. Next chapter we'll get into how really amazing it is. It's not just a random assortment of putting these elements this way. They really have they've gone over the models of it and different ways of building it. It's pretty amazing. So let's look at the stats of an atom. We have the symbol here. We always will have the atomic symbol. Everything has an atomic symbol. All the elements have an atomic symbol. It will be a capital letter. So one element will only have one capital letter. The atomic number is the smallest number. The atomic weight is the larger number. Here's the name, hydrogen. So don't think about top or bottom as far as the atomic number or the atomic weight, because each periodic table is different. I've seen periodic tables like this. I've seen periodic tables like this with the atomic weight on top or the atomic mass. I've seen it on the sides. So don't think about top or bottom because every periodic table is different. Usually you'll see periodic tables like this with the atomic number on top and the atomic mass on the bottom. But don't take that as always the case, such as this time. We don't have that. So you want to take the smallest numbers being the atomic number and the larger one being the atomic mass, usually the one with the decimal, and that's caused by isotopes, which we'll talk about in a second. Now, what is the atomic number? The atomic number is the number of protons. The number of protons would be the atomic number. So hydrogen has one proton. The protons will tell you what atom it is. Nothing else. It's the number of protons that tell you the atom or what element it is. The neutrons, the electrons don't tell you what the atom is. The proton make the atom. The proton is the atom. The proton will tell you the element. I really have to emphasize that. I just said it over and over, but it's important. The proton is like the heart of the atom. Okay, so all that other stuff is just extraneous. You know, someone might have cool hair or whatever, but that's just extraneous. It's what's in the inside that matters. It's the protons that matter. That tells you what the atom is. Atomic mass or weight, really mass, but is the number of protons plus the number of neutrons. So the protons and neutrons added together give it the weight. And that makes sense because the protons have a mass of 1, the neutrons have a mass of 1, and those two together will tell you how much that atom weighs. So in other words, I had a friend who always said in other words. He wrote a paper and I proofread it, and it said in other words like 20 times, and it was only a one-page paper. But anyway, in other words, the number of neutrons equals atomic mass minus atomic number, which is the protons. Atomic number is just the protons. So if we want to find the number of neutrons, we just take the atomic mass and we subtract the atomic number from it. Or we just take the atomic mass and subtract the protons for it. The same thing. We take the big number and subtract the small number to get neutrons. Now in a neutral atom, the number of electrons will equal the number of protons, so that makes it pretty easy. And we assume, when we look at that periodic table, all those elements are neutral. The electrons equal the protons. That means the negative atoms, the number of negative particles will equal the number of the positive particles, so they cancel out and they are neutral. So the number of electrons will equal the number of protons. So let's count the particles of the atom. Let's just take hydrogen, our first one. So we had 1 and 1.008. Now we're going to count the particles, which is pen. Now the protons equal the atomic number, so that's just 1. The electrons will equal the protons in a neutral atom, so that is also 1. It's the same as the protons. Now the neutrons equal the atomic mass minus the number of protons. Now what we can do for this, in this case, is we can round the atomic mass up to 1 or down to 1. So we can round up or down to figure out the neutrons. So it will be 1 minus 1 equals 0. So the number of neutrons in a hydrogen atom is 0. How about helium? Let's just try this. We have 2 and 4. Now I'm just going to do the rounding right now. I just wrote it right off of the periodic table, and I'm just going to do pen. Protons equal the atomic number. Electrons equal the proton, and this neutrons is the mass minus atomic number of protons, which is 2. So it's 2, 2, 2. Let's make this a little more challenging. Let's go to phosphorus. It has atomic number of 15. And we can round from 30.9 to 31. And we have protons, electrons, neutrons. The protons will be the atomic number 15. The electrons will be the same as the protons. The neutrons is the mass minus the atomic number, so that's 16. Let's try potassium. Okay, let's try it. It has 19 and 39. So protons, electrons, neutrons. 19, 19. 39 minus 19 equals 20. Let's try lead, Pb. So the protons, electrons, and neutrons, 82, 82, 207 minus 82, which equals 125. 125 neutrons. It's really important that we can do this just not even thinking about it. You can just look at one of these elements, not have to think, oh, what's the protons with the electrons, neutrons. So you just have to do this like in your sleep. So we'll be doing a lot of these just to get in the habit of looking at it and not having to think about it, because when we get further into chemistry, we can't take the time to think about it. So the question arises, why do the atomic masses have decimal? How can we have like a fraction of a neutron or a fraction of a proton? Why is the atomic mass in these decimals? Well, that comes from isotopes. So for example, here I am. This is my normal weight. But I also can exist as much smaller, much thinner. I also can exist much larger. So an isotope has, it's the same thing, but it has different masses. So these are all Mr. Barons, but this is the small or the thin Mr. Baron. This is the average, most abundant Mr. Baron. And this is the big Mr. Baron. It's still, the concept I want to get across is it's still me. It's still Mr. Baron, but I just have different weights. I'm the same person, but with different weights. And that's what an isotope is. It's the same element, but with different weights. And what defines an element? It's the proton that defines the element. So it's the same proton number. Isotopes are atoms of the same element, meaning they have the same number of protons, but have different weights. Same protons, but different number of neutrons. So all an isotope is, it's something that has different neutrons. And really neutrons just contribute to the weight for the most part. So it has different weights. It's an isotope. So we look here, carbon 12 and carbon 14. This is the atomic number. Here's the mass number. So the atomic number is a Z number, mass number A number. They both have the same atomic number, which means they both have 6 protons, which means they're both exactly the same. They're carbon. Carbon is 6 protons. But they just differ in the number of neutrons. You can count that. The white would be neutrons, the red would be protons. This is a proton, 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 proton. Hopefully you can see that. This is neutron, 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 neutron. So they both have 6 protons and 6 neutrons. Or this has 6 protons, 6 neutrons. But this one still has 6 protons, which makes it carbon, but it has 8 neutrons, which just makes it a big, heavy carbon. It's still carbon, but it's just heavy. It's an isotope. Iso means equal or same. Now another isotope example. This hydrogen, of course, hydrogen has 1 proton. Hydrogen 1, this is the atomic mass. No neutrons. Hydrogen 2, a proton and a neutron, because they both contribute to the mass. Remember, both the proton and the neutron contribute to the mass. The hydrogen 3 has 2 neutrons and 1 proton. They all have 1 proton, but now this gets heavy and because it has 2 neutrons. Isotopes of helium, 2 protons. They all have 2 protons, of course. But this one only has 1 proton. This one, 1 neutron. And this one has 2 neutrons. 2 neutrons, 1 neutron. They both have 2 protons though. Lithium with 3 protons, always 3 protons, but they differ in the number of neutrons. 3 neutrons here, 4 neutrons here. All right, another one, let's look at another view here of the helium. The isotopes of the helium, all helium has 2 protons, always, always. They just differ in neutrons. Okay, you can kind of think maybe the neutrons are kind of like the fat cells or something, or maybe muscle. Gives them more mass. The protons are their heart or their brain. Still the same person, but if they have more muscle mass or more fat, they're just heavier, but they're still the same person.